until I saw the glasses on the ground. So, the directions for 49 and 50 say, determine which graph shows the solution of the initial value problem without actually solving the problem. We could solve this differential equation, but they want you to use what you know about just thinking about, if this is the derivative, if we went back to the solution, we're going to add 1 to that exponent, yes? X squared, right away. We know there's going to be x squared, which means right away I would throw a out because it's not a parabola. I think we could throw c out because this is a negative. That means when we integrate it, it's going to be negative x squared. What we're going to start looking at today is thinking about what if we didn't even integrate it? What if we just thought about this having a negative, would it always have a negative slope? I don't know. No, because when we plug negative numbers in, it'd have a positive slope. And so what we're going to start thinking about today is, okay, if we plugged in negative values for x, we would always get positive y values, yes? Which means when x is negative, the function is increasing, because a positive derivative means increasing. And then when we plug in positive values, because it's negative x, this derivative is always negative. So for positive x values, the function is decreasing. And if you look at choice B, right, like that meets those requirements of saying when we plug in negative x values, this function is increasing and then it's decreasing. Well, I don't know that frowny face would be appropriate calculus talk there. But yes, like I would have said exactly what I said to begin with. I would have said when we integrate this, we would get x squared. It's negative, so I know it would be opening down. They were kind of wanting you to think more in terms of the derivative, but that's kind of what we're doing today, so don't stress too much about that. 49, I talked to a few people about just because, first of all, if I give you a derivative like this, that's one of those that you just have to remember, that's a 1. Right, that does not fit ln, because if you try to take the derivative of the bottom of that, it's not just 1. So you have to know that that's inverse tangent, right? And so that's what's harder about 49. And then again, I kind of didn't really follow the rules very well. I didn't actually work it out, but I did know that was inverse tangent. So then I had to think about what does the graph of inverse tangent look like, and then what does this point do to it. So just the answer to this would be arctan x plus c. So then you have to think about if you're trying to solve it by thinking of the graph, you have to remember what arctan looks like, which you probably don't remember. And you wouldn't have a calculator on this question. So the big question is, do you remember what tangent looks like?
Oh, so it's just...
Right, and then it just repeats itself wherever the asymptotes are. And so the inverse of that, like, flips the x's and the y's, but it's a little tricky because of this point right here, right? They're saying at 0, you get a value of pi halves. And normally, for arctan at 0, don't we get 0? So that's kind of, if we plug that in and solve for c, like it's going to move that up, which is why b has to be the right answer. Again, if we're talking about what do we know about the derivative in the back of the book, no matter what I plug into this function, do you agree I'm always going to get a positive number? Because it's 1 over 1 plus x squared, which means if the derivative is always positive, do you agree that means the function has to always be increasing? And so that's where you didn't even have to know it was arctan. If you just knew that this graph was always increasing, the only one that meets that requirement is b, and you didn't even have to be aware that it was arctan or what arctan looks like. And so today we're going to talk about what if we don't integrate it, or what if it's something really weird and we don't know even how to integrate it yet? What if we could just look at the derivative and base our graphs on what we know about the derivative at specific values? And so that's kind of what 49 and 50 were about. You could totally solve 49 and 50 by actually integrating and doing the graph part, which is kind of what I did. But the idea is maybe eventually today we'll figure that out. Other questions?
On number 6, is that function, well, I thought sine was 1 plus x squared, maybe?
It's 1 minus. The only one that's 1 plus is arctan.
Okay.
Arctan and arccotan. The rest of them are like sine and what? Arc sine and arc cosine, and the other one are x squared minus 1. Is that true? I'm not sure. Those are things that, do they show up all the time? No. But when they show up, you have to think about what are my options when it doesn't fit another rule that I have. And arctan is definitely one that shows up probably more often than the rest of them, in my opinion. Okay? Okay. I'm putting your notes out because we need some fancy graphs today. They seem like very short notes. What? Okay, so you probably saw those weird graphs when you did the homework over the weekend. Slope fields are kind of, in terms of AP calculus, relatively new topic. In the last 10 years, it's something that's shown up a lot. If you look, so here's what your book says about slope fields. The differential equation gives a slope at any point, right? Like if I said dy over dx equals 4x, then we could plug in different values of x and find the slope at each point, right? We've been doing that for a long time. So if I said, what is the slope at x equals 0, you could tell me the slope would be 0. We're going to start with some really nice slopes, and then we're going to get kind of crazy stuff here. What we're going to do is, instead of looking at integrating it and solving it, we're going to look, what if we just drew in the little slope segments for each point on a graph? We're not going to do a ton of points because you're going to see that it takes a while to do this sometimes. But using this, we can kind of sketch in what the curve would look like based on the slopes, all right? The really cool thing is there are computer programs that can do this, that can make a really large slope field. Jake so nicely has already programmed on his calculator a program that would do slope fields for you on a bigger scale. Drawing a slope field by hand would always be on a no calculator part of your test, so your calculator program wouldn't help you, but it's kind of a cool program that maybe tomorrow when we do a worksheet that we can share it together and do that. So the slope field. Slope field, they're going to give you a derivative or a differential equation, and then they're going to give you some points. I kind of can put a lot of points on here. We're going to start really, really simple here. If the derivative is 1, that means at every point on my graph, the derivative is 1. Do you agree with that? So what would its derivative, what would a slope of 1 look like? Yeah. So like I always kind of, like they give you these little dots to make, but like if I wanted to make a slope of 1 here, I always imagine like it would be like connecting this point with this point, but I'm just going to draw a little segment in to say at 0, 0, the slope is 1. And for this one, I would do that everywhere, right? Because the slope is always 1, because there's no x in the problem. So at every one of these points, I'm going to try to draw in the same slanted line of a slope of 1. That's exciting, right? I always try to imagine that these lines would connect to try to make them slanted the same amount. There have been free response questions, like part A, drawing the slope field for the given points on a graph like this, and they usually give you, it's usually a 2-point question. 1 point for all 0 or undefined slopes, because those are very easy to tell. 1 point for all other slopes, which means they're very lenient on if your line isn't, that looks like a slope of 2 more than a slope of 1. As long as you're consistent, they're going to give you your points for your slopes. Big idea is this is a positive slope, so you definitely don't want to make it going the other way. And there's usually never this many points on one graph, but we're getting the idea down. That is a slope field. We've drawn in the little slope segments through each point. And again, like I said, we're starting pretty basic here. But now, instead of talking about integrating this, which we could, but now we could talk about what if we sketch the curve in that would match these slopes that follows through this point. So it's kind of just like the homework that you did, but instead of giving you an equation, you use the slope field to sketch it. So at the point 0, -1, I know my graph has to cross as 0, -1. Using what I know, could I draw in a graph that matches having those slopes through 0, -1? It would just go like this, right? And right, they're not going to be this simple, but the idea is we can apply this to crazier slopes if we get the idea of it. And just to show you, what we're doing is exactly what we did. If you wanted to think about solving this, if you integrated both sides, right, you would get y equals x plus c. And then if you plugged that point in there, you would get that c equals -1, and you would get this equation for that line. Why are slope fields an interesting topic? Sometimes our differential equations are not easy to solve for, and so being able to sketch your curve with a slope field gives you an idea of what the graph looks like, even if we aren't able to actually do the integral over there. Let's do another one. Like this one. This was kind of weird because on your homework on Friday, did I give you any integrals that had y over there? dy dx equals 2y? No. We couldn't integrate this, just so you know, because if we tried to move this dx over here, that dx doesn't match that y, right? And then you had to move the y over there, and we don't do that yet. It's called separation of variables. We don't do that yet. But what we do need to do is find the slope at all the points on this graph. And there's kind of a lot of them. But the good news is, let's think about the point. And then let's think about the slope, which I'm going to say is dy dx. We don't necessarily have to write all these out, but we'll see if we can get a pattern going here. At the point 0, 0, could you tell me the slope? Does it matter what x is in this problem for what my slope is going to be? Because there's only a y over there in my differential equation. But at 0, 0, if I plug 0 in there, I'm going to get a slope of 0. Could I go as far to say at any point x, comma 0, my slope's going to be 0? Do you follow that notation? So could I say at, where does y equal 0? On the x-axis, y equals 0? My slope would be 0, which means it would look like a straight line. Right? Kind of hard to draw that in sometimes. What about, I'm going to go with just x's if you're okay with that, instead of putting an actual point. At any x value, but when the y value is 1, what's my slope going to be? Because 2 times 1 is going to have a slope of 2. What's the slope of 2 going to look like compared to a slope of 1? Steeper, right? And again, for me, sometimes I think about actually like what would the line look like when the y value is 1, which means this whole line here is going to have a slope of 2, which means like, what would you do? If you went down 2, back 1, it'd be like connecting this line to this line. Does that make sense? Or you could just draw a steeper line than 1. I don't know. I'm really bad at drawing these sometimes. Well, does that look steeper than 1? Yeah. Because 1 would be like to there, so that would be like, I don't know. No, not steep enough. What do you think?
I think it was fine.
Not. Oh, that's terrible. I'm just going with it. I overthink my slopes sometimes. What about the next line up? Y would be 2. So 2 times 2 would be a slope of 4. What's the slope of 4 going to look like? Really, really steep, right? Like not a vertical line, but steep. So like, I don't know. See why people use computer programs to do this? Here's what would be looking for, and here's what the AP people are going to be looking for. This should be steeper than this, right? They should both be positive. So as long as you're showing that, like, you would get credit for that. What's going to happen on the bottom? Yeah, they're going to be negative now, right? Because it's -1, so it's like at any x value, but when y is -1, we're going to get -2. And when y is -2, we're going to get -4, which means we're going to be going the other way. So that'd be like connecting of these two lines. Try to be consistent, but it's just really hard. And -4 is going to be like 4 up to there, like that'll be like really steep. Maybe, roughly speaking. Here's what's kind of cool about looking at slope fields, because here's what a lot of your homework is. You're going to be matching the derivative up with the slope field, and they get really confusing sometimes. But if there's only a y in the derivative, how could you tell if the one you're matching up with is only a y in the derivative? Let's do the next one that only has an x in it, and then we'll come back to that question. How about that? Okay. So notice this one only has an x in it, which means when I'm picking all my points, I don't really have to pick all of these points, right? Because it doesn't matter what y is, the x's are going to be what changes my slope every time, yes? So I'm going to look at my point, and then I'm going to look at my slope. So let's just start at like 0 first. So let's start when x is 0, doesn't matter what y is, what's my slope going to be when x is 0? 1, because 0 plus 1 is 1. Where is x always 0? Vertically, right? The y-axis. So on the y-axis, my slope should all be 1. And again, that's like kind of connecting this point to this point is what you're thinking about when you're doing it. And you don't actually have to write this chart out. Sometimes there might be both x and y in it if it's like it helps to write it out maybe. But as long as your slopes, like this is what gets graded, that's just kind of your work if it helps you. Because you could just say in your head, like, when x is 1, that will be this whole line. What's my slope going to be on this whole vertical line? 2. Because when x is 1, doesn't matter what y is, 1 plus 1 is 2. Which would be like up 2 over 1, so it would be like, I think that one, and that one, and that one. And when x is 2, 2 plus 1 is 3. Yes, which means, again, we're just kind of getting steeper as we go. And we just want to kind of show that we're getting steeper and that we're positive is kind of what we're looking for. Don't have to be perfect as you're going. Maybe, I don't know. And what's going to happen on this side? Yeah, so at -1, -1 plus 1 gives me 0. 0 slope is just a straight line like this. That's my favorite one. Or undefined is also my favorite. What's undefined slope look like? And then when I plug -2 in, I get -1, which means like up 1 over 1 like this. So roughly speaking. When I'm grading these, I look for your zero slopes, and I look that your negatives and positives are going the right way. Like, that's a big, big problem, if they're not. But then you just kind of look for that, oh, I can see this is getting steeper. It's flattening out to zero. This side's going to, if we kept going, would get steeper as well. Yes? So let's go back to my other question. If your job on your homework was matching, and they gave you a bunch of slope fields, and they gave you a bunch of derivatives, how could you tell by looking at the slope field whether it had just x in it or just y in it? So look, this one's just x. This one's just y. Look horizontally on this one. Are the slopes the same all horizontally? It doesn't matter what x is, right? And look on this one. What happens vertically? The slopes are all the same. So if you see that the slopes are all the same one way or the other, then you can do like process of elimination. Because some of these are going to have both x and y in them. And if there's both x and y, do you agree like each of these points could be a different slope? It's a little crazier to do that. But that's my first thing I do when I'm matching, or on multiple choice question on the AP exam. There's usually a multiple choice question that they give you a slope field and they ask you to match it up with an equation. The other thing that I look for is where it's zero, right? If I see that this has a zero at -1, well then I go to all my options and say which one would make a slope of 0 at -1 and can kind of match up from there. And so don't feel overwhelmed by those matching ones because sometimes people do it first. Just look for some strategies there. Another thing that's really cool about this is a little bit harder than the first one. What if I asked you to sketch the curve that passed through the point -1, 0? So they give you a point, because here's the idea. This slope field represents every possible solution. Depending on what C is, that changes where your curve would be. So if they give you a point, graph that point, and then use the slopes to try to draw the curve in. And yes, sometimes you can cheat a little bit and actually think about what the integral would be. But sometimes you can't because it's really complicated. But I'm not even going to look at the equation right now, but just think about it. If this has a slope of 0, what do we know on our graph when the slope is 0? It's a turning point, right? What do we know about our graph when the derivative is positive? It's increasing, and what do we know about our graph when the derivative is negative? It's decreasing. So if this is my point, look what's happening over here. These are positive, and they just keep getting more and more positive, which means I could kind of draw this as it's going to be going up, and it's going to be increasing, and it's going to keep getting steeper and steeper and steeper. You agree with that? And over here it's decreasing, and I only have one side here, but over here it's decreasing, so it should be decreasing and coming down through here. Here's what I want you to get about drawing these curves in. Just because we have all these lines in here, you don't have to make your graph like touch exactly at one of those lines. Sometimes it might fit perfectly, but they're just giving you like an idea. Does that make sense? So like if I was going to draw this in, I'm going to say 0 here, and then it's going to be increasing. So I'm just going to kind of draw it in like this, and this side's decreasing, and I'm going to draw it in roughly like that. It doesn't have to necessarily hit one of those slope field things. Does that make sense? Because I always feel like it should, but it doesn't. It doesn't. Because really, could I draw the slope field in right here too? You see what I'm saying? Like they just give you certain points to draw it in, but technically like these little dash lines are like everywhere on this line. Does that make sense? But I'm with you. Like I always wanted to touch those, but I just know from looking at solutions that they don't have to. Does that make sense? If we integrated this, would it look like a quadratic? Yeah. And so that's a nice way to check. What about this one? I didn't make you draw this one in because this one's a little crazier. We don't really know what this is going to look like if we integrate it, right? No. Technically, it's going to be an ln, but I'm not going to tell you why that's true right now. You should know that. But when there's something like this cut in the middle, and then it's different like this, it's kind of hard to think about drawing it in. So this is where the point really matters. If they gave us a point up here, then we would say, I don't know, I'm trying to think of a good point here. How about let's just do this. If my point was like this, This side is kind of showing, I don't even know, kind of like a horizontal asymptote, maybe? I don't know. This side's definitely increasing. Do you agree with that? This side, it's like what's happening here. These are hard. We're going to get better at this. I think if it was like down here, I would draw this in like this. But like, it's very questionable what's happening here, right? Here's where, like, we'll get there. Just don't stress too much about it today. I promise. That's why we're studying tomorrow on it. I would draw this in like this. Like, this side would be like this. What's happening here? I don't know. What? Yeah, it's weird. Asymptotes do weird things to us. I just want you to know for slope fields. So just don't stress a lot the Y one so much. Look in the back of the book some to help you, and we'll get better at it. I promise. Should we do one with both X and Y in it before I give you homework? Or maybe we should do one together from the homework? Some of them. It's the same thing. It's just X's and Y's together, right? Let's write our homework down and we'll try one together, okay? (29) through 32 are the ones that they want you to draw your own slope field, which means they want you to make a little graphic. We'll do one together. We'll not do the easy ones, like we'll do one of the hard ones. And then 35 through 40 are matching, and again, use process of elimination to help you on those. And then 51 and 52 give you a slope field, and they ask you to think about could you find the equation that goes with it. And then 61 is multiple choice. But 29 through 32 are going to be the rough ones. And on 29 through 32, they give you a whole lot of points. We're going to cut that down, and let's just do those, like, instead of going to 2, let's just do the x-axis from -1 to 1. And then the y-axis from -1 to 1. They have you doing 12 points, and I'm going to only have you do 9 points. And let's do 31 together, so then I make you do another even one by yourself. Right, 2x plus y, which means we actually are going to have to think about what the slope at each point would be. And the direction on this says use slope analysis, not your graphing calculator. And so I'm going to make a graph, and you want to make one decent size so you can draw these slopes in. But we're only going to go -1 to 1. So like this is just going to be like -1, 1, -1, 1. And then draw those little circles on your graph. Like these are the 9 points you're going to make slopes for. If you wanted to, on the other ones, if you want to draw that in pen, and then you can draw your slope fields, like your slope lines in pencil, so then if you erase or whatever, I just do it on pencil. But that's what you're going to do for 29 through 32. But if there's both an x and a y in it, you do actually have to think about every point. If it helps you, draw the x, like the chart out, and you can actually do each one, or you can just do it in your head. You're just plugging in these points into the derivative. And so, again, I like to write it like this. It's like an xy chart, only it's a point derivative chart. You can start wherever you want. I tend to start at 0, 0. And if I plug 0, 0 in there, I would get a slope of 0. Yes? So if you wanted to, you can make your chart for all 9 points, do your slopes, and then go back and do it. Or you could just go through each point and do the derivative and plugging those points in. Does that make sense? So at 0, 0, the slope is 0. At 1, 0, that would be a slope of 2. Do you agree with that? so no rhyme or reason, I'm just going along the x-axis here. At negative 1, 0, that would be a slope of negative 2. Yes? Anybody have a question on where I'm getting these values from? Going up at the point 0, 1, that would just be a slope of 1. At the point 1, 1, that would be a slope of 3. It's going to be pretty steep, right? Like, I'm going to say like that. At negative 1, 1, that would be a slope of negative 1. Is that true? So that's the same as this one? No, that was negative 2, wasn't it? Negative 1 would be not as steep as that. At 0, negative 1, this would be negative 1. Would this one be 1? At 1, negative 1 would be a slope of 1. And at negative 1 would be a slope of negative 3. Is that true? Negative 3. Which is really steep, but that way. It's really hard with 9 points to get a good idea of what the slopes look like, which is why it's kind of cool to see the computer-generated ones or the ones generated on the graphic calculator, because you can see, like, if we asked you to draw a graph in for this right now, just like the other one that we did, it's kind of hard because there's so few points, and we don't know what this is going to look like off the top of our head. It's not going to be pretty. It's not going to be a function, actually. It's going to be something that fails the point test, like that. So it's hard with the 9 points, which is why I like giving you the 35 to 40 where you match them. And notice on all of these that give you all of these points, they tell you the window there is going from negative 6 to 6 and negative 4 to 4. So the point that they have graphed on all of those is the point 32. So notice not each line represents like one on the graph. Like, just be aware of that. But when you see all those tick marks for the slopes, I think it's easier to trace your function in. So we'll see what questions we have tomorrow. I have a worksheet day tomorrow just because I have another day of doing slope field stuff, because I think it's important to talk about the relationship between the derivative and the slope field, and then what if they gave me the actual equation of the slope field and matching it. So it doesn't mean there's a homework quiz tomorrow. It just means we're going to spend another day talking about this stuff because it's kind of a different idea. But try these today, work them out. 35 to 40 would be kind of the tough ones, I think, of throwing it in, and then we'll go from there tomorrow. Okay? And you even have time to work today.